guys, Professor Brown here, and in this video we are going to be doing some sample calculations concerning the properties of light. We'll be calculating for frequency and wavelength, and we will also calculate the energy of some individual photons. The first problems we are going to work on concern calculating wavelength given the frequency. The formula we are going to want to use for these problems is C equals lambda times nu, where nu represents the frequency given in hertz or per second. The lambda represents wavelength given in meters, and C is the speed of light, which is 2.998 times 10 to the 8th meters per second. Our first problem here says microwaves have frequencies in the range of 300 megahertz to 300 gigahertz. Calculate the wavelength of a microwave with a frequency of 2.45 gigahertz. So to solve this problem, we're going to use our formula, C equals lambda times nu, where lambda is the wavelength and nu is the frequency. We know that C is 2.998 times 10 to the 8th meters per second. We are asked to find the wavelength, and we're given a frequency of 2.45 gigahertz. So this formula is calculated using the unit hertz for the frequency. That is why the speed of light is given in meters per second. A hertz is 1 per second. One of anything happening per second is happening at a frequency of 1 hertz. And so to calculate this correctly, we need to convert our frequency of 2.45 gigahertz into regular hertz. And so 2.45 gigahertz times the fact that there is 1 times 10 to the 9th hertz in 1 gigahertz. If we calculate that through our calculator, we will see that the result is 2.45 times 10 to the 9th hertz is our frequency. So we've converted our gigahertz frequency to hertz frequency. Now we can throw it into our speed of light formula and use that to determine the wavelength of our microwave. So we will write 2.998 times 10 to the 8th meters per second is equal to lambda times 2.45 times 10 to the 9th hertz. I will divide both sides by 2.45 times 10 to the 9th. That means lambda will be equal to 2.998 times 10 to the 8th divided by 2.45 times 10 to the 9th. And that returns a result of 0.122 meters. So our microwave has a wavelength of about 12.2 centimeters. Our next example reads, visible light has frequencies in the range of 4 times 10 to the 14th hertz to 7.5 times 10 to the 14th hertz. Calculate the wavelength of a beam of visible light with a frequency of 6 times 10 to the 14th hertz. We may notice that they were nice to us in this problem. We were given a frequency in hertz, so we don't have to do any conversion. We can jump straight to the calculation using the speed of light formula, which again is C equals lambda times nu, where C is 2.998 times 10 to the 8th meters per second. Lambda is our wavelength that we do not know, and it is given in meters. Nu is our frequency in hertz. So if we write our formula filled in with our variables that we know, 2.998 times 10 to the 8th meters per second is equal to some wavelength we have yet to determine times a frequency of 6 times 10 to the 14th hertz. I can solve that algebraically by dividing both sides by the 6 times 10 to the 14th hertz. Dividing that in my calculator, 2.998 times 10 to the 8th divided by 6 times 10 to the 14th gives me a result of 4.99 times 10 to the negative 7 meters. And without doing the conversion just quickly, that's about 499 nanometers for this particular source of light. Our next example here says X-rays have frequencies in the range of 3 times 10 to the 16th hertz to 3 times 10 to the 19th hertz. Calculate the wavelength of an X-ray with a frequency of 6.34 times 10 to the 17th hertz. So again, in this problem, they've been nice and they've given us the hertz, or the frequency rather, in hertz, and not forced us to do a conversion ahead of time. We can jump straight into our C equals lambda times nu formula. We know that C is always equal to 2.998 times 10 to the 8th meters per second. we're solving for a wavelength in this particular example, and we know that the frequency is 6.34 times 10 to the 17th. So solving this problem involves dividing both sides by 6.34 times 10 to the 17th. I should use my units there, hertz and hertz. 6.34 times 10 to the 17th hertz. And our wavelength will be determined by taking 2.998 times 10 to the 8th dividing by 6.34 times 10 to the 17th gives us a result of 472.9 times 10 to the negative 12 meters. Our next few examples will involve calculating frequency given the wavelength this time. We will still be using the formula C equals lambda times nu, with nu representing the frequency, lambda representing the wavelength, and C representing the speed of light. Our first example in this set asks, radio waves have wavelengths in the range of 1 millimeter to 100 kilometers. Calculate the frequency of a radio wave with a wavelength of 1.5 meters. This is one of our C equals lambda times nu style problems. This time we know the lambda, we don't know the u. We're going to solve for the nu. We always know the speed of light. It is 2.998 times 10 to the 8th meters per second. That equals the lambda that we know. Luckily for this problem, we're given the wavelength in meters, so we don't have to do a conversion to meters, so we can just put 1.5 meters times the frequency that we have yet to determine. To solve this, we're going to divide both sides by the 1.5 meters term. And if we punch that in our calculator, it will be 2.998 times 10 to the 8th divided by 1.5. And that gives me a frequency of 2.00 times 10 to the 8th. And the frequency, or the units rather, on frequency is hertz, or per second if you rather, s to the minus 1. Our next example of calculating frequency given wavelength reads, infrared radiation has wavelengths in the range of 700 nanometers to 1 millimeter. Calculate the frequency of infrared radiation with a wavelength of 800 nanometers. So this question is going to ask us to use the C equals lambda times nu formula again to solve for the frequency given the wavelength. However, this time our wavelength is given in nanometers, and for the problem our wavelength needs to be meters. So the first we're going to do is convert our nanometers to meters. So we have, the problem says calculate the frequency of infrared radiation with a wavelength of 800 nanometers. So 800 nanometers, we need a conversion factor. There is 1 times 10 to the 9th nanometers in every 1 meter. So to convert 800 nanometers to meters, I need to divide by 1 times 10 to the 9th. So I will punch in 800 divided by 1 times 10 to the 9th. 1 times 10 to the 9th, 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 1 times 10 to the And my calculator tells me that is 8 times 10 to the negative 7 meters. So then I can fill in my formula. 2.998 times 10 to the 8 meters per second is equal to 8 times 10 to the negative 7 meters times some frequency. To solve this, I am going to divide both sides by 8 times 10 to the negative 7. And I can determine my frequency by taking 2.998 times 10 to the 8th, dividing by 8 times 10 to the negative 7. And my calculator tells me the frequency of that particular radiation would be 3.75 times 10 to the 14th hertz. Our next frequency calculation example reads, ultraviolet light has wavelengths in the range of 10 nanometers to 400 nanometers. Calculate the frequency of ultraviolet light with a wavelength of 250 nanometers. So this problem looks much like the last one. The first thing we're going to need to do is make the conversion from nanometers to meters. In this problem, we're told our radiation has a wavelength of 250 nanometers. I use a conversion factor, the fact that there is 1 times 10 to the 9th nanometers in every meter means I will need to divide 250 by 1 times 10 to the 9th. And that is 2.5 times 10 to the negative 7 meters. So when I set up the formula, C equals lambda times nu, 2.998 times 10 to the 8 meters per second equals 2.5 times 10 to the negative 7 meters times the frequency we have yet to determine. We'll divide both sides by 2.5 times 10 to the negative 7 meters. Making our frequency uh, 1.199 times 10 to the 15th hertz. Our next set of questions is going to involve calculating the energy of a single photon. We're going to be using a new formula this time, the formula that Einstein proposed after observing the photoelectric effect and explaining the photoelectric effect. The formula is the energy is equal to Planck's constant times the frequency. The frequency is like it was before, given in hertz or per second units. H is Planck's constant, which has a value of 6.626 times 10 to the negative 34, and the unit there is joule seconds. So the joules and the seconds are multiplied, and that's what the dot is. So we don't say joules per second, we just say joule seconds. And the energy, therefore, is calculated in joules. Be aware some of the problems may give you the wavelength instead of the frequency and force you to use the previous formula to convert that wavelength to a frequency before you can solve for the energy of the photon. Our first example here says ultraviolet light has a frequency of 7.5 times 10 to the 15th hertz. Calculate the energy of a photon of this ultraviolet light. So we just saw on the previous slide that energy is equal to Planck's constant times the frequency. Planck's constant has a value of 6.626 times 10 to the negative 34 joule seconds. Our frequency is given to be 7.5 times 10 to the 15th hertz. This is a pretty straightforward calculation. We just have to take 6.626 times 10 to the negative 34. Multiply that by 7.5 times 10 to the 15th. And the calculator tells me that the energy of one of those photons will be 4.97 times 10 to the negative 18th joules. Our next example here says gamma rays have extremely high frequencies. Calculate the energy of a photon with a frequency of 1.2 times 10 to the 20th hertz. We know that energy is equal to Planck's constant times that frequency. So energy therefore is equal to 6.626 times 10 to the negative 34 joule seconds. We're going to multiply that by that frequency, 1.20 times 10 to the 20th hertz. Therefore, the energy of one of these gamma ray photons is given by 6.626 times 10 to the negative 34 times 1.20 times 10 to the 20th for a total of 7.95 times 10 to the negative 14th joules. Our next sample here reads X-rays have a wavelength of 1 nanometer. Calculate the energy of a photon of this X-ray radiation. So this problem is one of the first examples to give us a wavelength and not the radiation. If we look at the energy formula, E equals hv, we notice that there is no wavelength term in that formula. However, we do know a formula to figure out the frequency given the wavelength, so we're going to have to do that first. Furthermore, this problem doesn't give us a meters for the wavelength, it gives us a nanometer measurement for the wavelength. So the first thing we need to do is convert the nanometers to meters. So 1 nanometer times the fact that there is 1 times 10 to the 9th meters in every 1 nanometer means that 1 nanometer is 1 times 10 to the negative 9th meters. So I can then take that and use the first formula, C equals lambda times nu, substitute in 1 times 10 to the 9th meters for lambda, and then I can solve for nu by dividing both sides by 1 times 10 to the negative 9th. So my frequency, therefore, is 2.998 . times 10 to the 8th divided by 1 times 10 to the negative 9. And so the frequency is 2.998 times 10 to the 17th. I can then use that frequency to solve for the energy by plugging it into the energy formula, E equals hv. So then E becomes 6.626 times 10 to the negative 34 joules seconds times that frequency, 2.998 times 10 to the 17th hertz. After punching that in my calculator, I find that there is approximately 1.99 times 10 to the negative 16th joules of energy in one of these photons. We've got another example here where we are going to calculate the energy, but we've been given the wavelength and not the frequency, so we need to use that wavelength to get the frequency first. So we are going to start by writing down the formula C equals wavelength times frequency, 2.998 times 10 to the 8th meters per second is equal to the wavelength, and this time 500 nanometers. I'm just going to do the conversion off screen this time. 500 nanometers is 5 times 10 to the negative 7th meters. And we're going to multiply that by the wavelength to determine the speed of light. We can solve this by dividing both sides by 5 times 10 to the negative 7 meters. That will indicate that my frequency is 5.996 times 10 to the 14th. And then I can use that and plug it into my energy formula. E equals Planck's constant times the frequency. E will equal 6.626 times 10 to the negative 34 times the frequency, which we have determined is 5.996 times 10 to the 14th. The energy will therefore be 3.97 times 10 to the negative 19th.